Is a very exciting lecture because we are going to be seeing quantum algorithms for the first time, which I think is probably what many of you signed up for this class hoping to get to. So today we're going to do really a big introduction of quantum algorithms and go through the landscape of quantum algorithms, look at a few of the main historical algorithms that are kind of the basis for really most of the algorithms people are working on today. So it's going to be a lot of fun. Also, today is my last lecture, so uh, I I'm sad that my teaching will be finishing up today, but hopefully it's a great lecture and we have a lot of fun. So with that, I will pass it over to Rachel for some announcements.
I don't know how I follow that up. I'm guessing most people did not realize we'll have several lectures with Amir after this. And so I hope you just really enjoy this last major lecture with Fran. We've heard such incredible kind words from everyone in the course about how much made an impact on your journey learning quantum computing. So thanks to Fran. Just two very quick announcements. So as a reminder, we'll be taking a spring break for this course, April 4th and April 11th. Those 2 weeks, we will not have lecture or lab. So we have today, we'll have a lecture next Sunday, and then we'll be on break following that. So keep an eye on Canvas just to make sure you get those dates correct. But if you're planning for vacations or holidays at home, keep that in mind. And then just a note about today's lecture. So Fran's going to give about an hour and a half lecture, and then Akshay is going to help with a bit of a Qiskit and Python basics review. So for those who are still learning Qiskit or struggling with some of the fundamentals that we introduced at the end of first semester, we're going to do a review, optional if you want to stay or not, and we'll post that recording as well. But just look out for that. We'll transition with about 30 minutes left to go of the regular lecture time. And I think that's it for me. With that, we will learn all algorithms with Fran.
All right, thanks, Rachel. And like Rachel said, we'll be switching to an optional programming review at the end of class. So we have quite a bit of content to cover in the next hour and a half. So I'm just gonna plow through. We've seen this slide several times already, and now is really kind of when we come to the end of our sort of introductory quantum computation lecture series. Over the next few weeks, Amir is going to be taking the idea of quantum algorithms that we're going to introduce today, and kind of teach you guys about some advanced and state-of-the-art algorithms in a lot more depth. Today, we're kind of just familiarizing ourselves with what a quantum algorithm actually is, ways that we can sort of describe their performance, and talk about how they relate to different classical algorithms. So the lecture on my end before we get to that programming review will be broken up into two kind of key parts. We'll start about talking why algorithms are important, then just talking about what an algorithm is in the general and classical computing sense. And then we'll spend quite a bit of time focusing on how we can actually characterize algorithmic performance. So talking about algorithmic efficiency and stuff, so that we have a means kind of to compare different algorithms, especially comparing classical to quantum algorithms. And then the sort of second part of the lecture will be really focused on looking at a few of the main ideas in the quantum algorithms landscape. So that should be a lot of fun. But before we get there, I kind of just want to take a quick step back. We've really spent a lot of time this semester learning about the technical details of quantum information, computation, learning quantum mechanics, all this technical stuff. And I find sometimes that myself as a student, right, when you get too deep into the weeds, you can sometimes lose the big picture, the motivation. So I just wanted to take a step back and ask, why do we care so much about building quantum computers in the first place? What will they actually be useful for? And so the motivation I'm going to talk about right now is just one of many. but it's one I've been thinking about a lot recently because I actually recently ordered this new book that came out by Bill Gates, How to Avoid a Climate Disaster. It's a really, really good read. If you're like me and don't have really any background in environmental science or chemistry or biology, and I think it does a really great job of describing a lot of the main issues with climate change, and really how we need to think about the climate going forward, to really save the planet. And one interesting thing that recurs throughout the book is this notion of these two numbers, 51 billion and zero. 51 billions is the sort of how many tons of greenhouse gas the world currently adds to the atmosphere annually. So this is kind of how much we're polluting right now. And by the year 2050, we need to aim to have net zero emissions. Going from 51 billion to zero is a pretty big drastic change. And 2050, that's not too far away. We don't have as much time as many people may think. So this poses a really big challenge, right, to not only us as individuals, but to society and humans as a whole. Um, and so uh, in order to kind of achieve this transformation to save our planet, right, we're going to need a lot of innovation. We're going to need innovation in policy, economics, institutions, and in technology. Um, and so these problems are so hard that we can't solve them really just by talking or thinking about them. We need to be able to compute and get concrete numbers. But because these problems are so hard, we couldn't do them by sitting around calculating things by hand. We need to do computation with state of the art computers. Um, and there's all kinds of problems that you could specifically think about relating to climate change, which are very computationally intensive, like modeling the atmosphere, predicting energy usage, solving for efficient material properties, strategic use of different renewables, like where to put different types of renewables, monitoring emissions, or even just calculating green premiums. Um, these are super, super hard problems to solve, and we need to be able to perform things like optimization, complex simulations, stuff like that. And so really to achieve the innovation that we need to solve the problem of climate change, computation is going to be our workhorse. Now, as I emphasized, right, uh, these computations will not be easy. Scientists have worked extremely hard for several decades to develop algorithms, which is what we'll be focused on today, which run on classical computers to attempt to solve these types of hard problems. However, some of these problems are computationally so hard that even if we took the world's largest supercomputer, which I think right now is Japan's Fugaku supercomputer, it would still take the age of the universe to compute, like to basically run the program that performs the computation you need to solve the problem. So for some of these problems, although we really want to, and in the case of climate change, need to solve them, we just don't have the computational power available with the machines we have today, even the very best ones in the world. And so this is one of the motivations, right, for quantum devices and quantum computation as a whole, right? A key goal of quantum computation is leveraging our added resources, right, that we've talked about a lot this semester, entanglement, superposition, quantum interference, to design what are called quantum algorithms, which are far more powerful than any classical algorithm, and enable us to efficiently solve certain types of problems. So I really emphasize here certain types of problems because the way we're looking at quantum computers right now, it's not gonna like make your email drastically faster or sort of day-to-day tasks. The idea is really to use them for these computationally intensive, challenging problem by designing specific algorithms which leverage our quantum resources. But as we'll see in the lecture today, these algorithms are pretty complicated, right? Quantum computing is complicated and tricky to design, but we'll learn about some techniques people have developed over time to create these quantum algorithms. And I just wanted to also note, right, that actually the original idea for quantum computers came from this man here, Richard Feynman, a Nobel laureate, who basically proposed the idea of simulating quantum on quantum. The idea being, right, if you want to simulate quantum phenomena, why simulate it on a classical system, right, where you have to code up actually the laws of quantum mechanics and then simulate that classically to then get out a quantum result? Why go through all those layers of abstraction when you could instead just build a quantum device and simulate quantum on that directly? And we'll get back to this actually at the end of the class. So kind of in preparation for today's lecture, right? So far, we've really focused on quantum mechanics and kind of the fundamentals of quantum information. So the notion of the qubit and thinking of quantum particles as bits of information, learning about protocols, which are kind of quantum information processing. But in today's lecture, we're going to focus on quantum algorithms, which is really where the computation part of quantum computation comes from. So this should be a lot of fun, and this is actually very relevant to the research I'm interested in doing my PhD. So hopefully you guys will pick up on some of that excitement. Now, before we can get to quantum algorithms, right, we need to start off by defining what an algorithm is, and we'll look at it in the classical sense. So to sort of take out the dictionary definition of an algorithm is simply a set of instructions or rules that, especially if given to a computer, will help to calculate an answer to a problem. So there's really three key steps, right? You have a set of inputs that you'll perform computation on using a set of carefully designed instructions to get some desired output. Now, algorithms aren't really limited to computers. For the rest of today's class, we'll be thinking of them in the sense of computers, but you've actually experienced algorithms all the time in the real world in your day-to-day life. One example is a recipe. So sort of following the structure we saw in the last slide, right? If you think about a recipe as an algorithm, the three kind of components of this algorithm are the inputs, which are just the ingredients. So your onions, peppers, tomatoes, pasta, all of that. And then you take all these inputs and you perform computation on them. And so the computation will be you as the chef going and actually preparing the dish. So you'll have to cut up the pieces, you'll have to heat the water, mix everything together and put it on a plate. And then your output, right, of this computation is the pasta dish that then you and your friends and family can enjoy. But as I mentioned, right, in today's class, we're going to be focusing on the computer science notion of an algorithm. And as it turns out, most of computer science really revolves around developing efficient algorithms, right? It's one thing to design an algorithm that gets the job done, but generally speaking, we are not patient. The reason why we designed computers in the first place, right, was so that they could do computation better and faster than we as humans can, right? So a key goal is developing efficient algorithms, and people have worked on this for quite a while, and they're kind of mainstream in all of the technology we use, right? So things like performing a Google search, using maps to find directions when you're trying to drive to some neighboring city, or even when Spotify and Netflix give you recommendations for songs or movies. These are all examples of algorithms that are happening behind the scenes to make that happen. And so we've been talking about algorithms pretty abstractly now, right? But let's kind of see what's going on behind the scenes and how you can actually implement an algorithm in Python. So The algorithm that I'm going to introduce now and focus on for the next few slides is an algorithm to perform search. So the key idea here is that we will have an input, which is a list of animals, and our goal is to figure out where the entry dog is in our list. So we don't know beforehand, but we've queried a computer and we want it to tell us what index of the list the dog is at. So in coding up an algorithm, performing algorithmic thinking, one way you could tell your computer to do this is by taking in the list and checking every single index until it finds dog. So the computer would start by looking at the first index and then asking, is this a dog? If it was, then it would just report the index 0. But we see, right, that it's a frog. So it says no, and then moves to the next index. And it asks, is this a dog? Nope, it's a cat. Let's move to the next index. Is it a dog? No, it's a tiger. Next index, it's an elephant. And then finally, by the time it gets to the fifth index, it's found the dog. But of course, we're using our 0 indexing. So the computer will output the dog index, which in this case is just equal to the number 4. So all we've done, right, is we've iterated through every entry of the list and just checked whether or not that entry of the list contained the dog element or not. So to show you guys even more concretely what this would look like for a computer, I wrote up an implementation of this algorithm in Python. Oh, one thing I forgot to mention, right? This algorithm is actually called linear search, right? Because you're just stepping along, checking every entry, and we'll kind of see in a bit why as well this term is linear. But going back to the code, right? So I implemented this myself. You're not expected to know how to implement algorithms in Python. I just did this to make it a bit more concrete for all of you guys and to see how you could actually go about implementing an algorithm using Python. So basically, this first line here, I'm just defining our input list. And then this set of lines here is really where the computation happens. Essentially, I'm calling this enumerate function, which basically gives us the animal and index, and it just iterates through them in this for loop, sort of sequentially. And so all that I'm doing, right, is I have this if statement here, which just checks if the animal is a dog or not. And if the animal is a dog, then it sets our dog index to the current index it's checking. If it is not a dog, then it just moves on and checks the next one. And so basically to verify that my algorithm worked, I included some print statements at the end. And when I tried actually running it on Python on my own computer, I got this output here, and it basically told me that my dog index was 4. And when I printed out that index directly from the list, I got the output dog, which confirmed that my algorithm worked. All right, so we just saw an example of an algorithm, and we confirmed that it worked, right? But how can we tell whether or not that algorithm is good or bad? I want to ask, what does good even mean in the context of algorithms? What are the characteristics of a good algorithm? And then this is an important question to ask, right? Because if we don't know what constitutes a good algorithm, how could we then compare different algorithms and say whether or not one is better than the other? So kind of the rest of our discussion of classical algorithms will really be focused on asking this question, is my algorithm good? And how can I say whether or not one algorithm is better than the other? Essentially, how can I compare different algorithms? So now we step into the realm of characterizing algorithm performance. And it turns out that in designing an algorithm, we really have two key goals. Irrespective of the input to our algorithm, so it could be a longer input, like a bigger list in the case of our linear search algorithm, or a more difficult input. So if dog comes later in the list, right, it'll take longer to find. Versus if it was the first element in our list, we'll find it right away. So we can attribute a sense of difficulty to the input. Oops. So irrespective of what the input is, the algorithm should have two key properties. It should be able to solve the problem correctly, right? An algorithm isn't very useful if it tells you the wrong thing, right? If that was the case, if we had no guarantee that it was doing the right thing, you probably wouldn't want to use it if it was for something really important. And so that's the notion of accuracy. However, we're going to assume that for now, all the algorithms are correct. We're super geniuses. We always code up our algorithms properly. There's never an issue. Our algorithms always work. And the thing that we're interested in today is the notion of efficiency, or talking about how fast we can solve the problem, right? So if you have an algorithm, if it runs more quickly, you could say that algorithm is better, right? Because in an ideal world, our algorithm would run instantaneously. We wouldn't have to wait anything, just get an answer immediately. But of course, when you write up an algorithm, at the end of the day, it has to run on physical hardware. And there's limitations as to how fast that can happen based on the speed of the core in your processor, all that kind of stuff. And so our goal as computer scientists is to come in and try and design the most efficient algorithm that will run as quickly as possible. So now that we've narrowed our focus for today onto quantifying algorithmic efficiency, how do we actually go about that? And so one thing that you might think to do, which I'll call the sort of naive idea, is to basically just report the algorithm runtime on your computer for a specific input. So that example that I showed you, right, a few slides ago, I took that code, I ran it on my laptop, I added a couple more lines of code basically to time it so that I could see how long it took. And I saw that my algorithm took 0.472 milliseconds. But that kind of begs the question, what does this number mean? And how could I compare this number to the numbers generated by different algorithms? Potentially there are some problems in kind of using this. And I just wanted to take a quick minute where I'll just let you guys think about on your own what some potential problems are using this naive idea. All right, I'm seeing some great comments in the Q&A section of people coming up with different ideas for why this might be a bad metric. And actually a lot of you were hitting at just the right places. So to lay it down concretely, there are a few issues. I boiled them down to three kind of key issues with this naive idea. So the first problem is that runtime is a hardware dependent metric. If I have access to the world's largest supercomputer, the one in Japan, I will most likely be able to run whatever algorithm that I generate more quickly than I can say on my laptop, right? But that isn't dependent on the algorithm itself. That's dependent on the computer hardware, and hardware is always changing over time. So we don't necessarily want to characterize how good an algorithm is by the hardware that we're running the algorithm on. We want our metric to tell us how good the algorithm is independent of hardware. The second key issue is that runtime depends on the input difficulty. So as I hinted at before, right, if you have this list and dog is the last entry in the list, it'll take a lot longer for your linear search algorithm to find than if dog were the first entry of the list. The third kind of key problem is input size, right? If I gave you a list that had 20,000 animals, it would probably take a lot longer to find the dog in that list than in this case where we only had six items in our list, right? Because in all likelihood, it's going to be after the sixth entry. And to sort of illustrate these ideas, right, in this plot here on the right, I made a plot of our linear search algorithm and the different runtimes I got as I just increased the number of animals in the list from 0 to 100,000 and kind of calculated the runtime there. In this case, I didn't actually randomly change the location of the dog in the list, because then it would have just been really sporadic. In this case, I was just making dog the very last entry in the list. But you see that even then you get huge fluctuations, right? And that just has to do with specifics of the hardware and how data is stored on your chip, as well as, right, we see that it increases kind of as a function of input size. So if I were only to try and characterize the performance of my algorithm based on a single input, like maybe 20,000, I would get a very different runtime, right, than if I were to try and characterize it based on an input of length, I don't know, 80-ish thousand. So this is all kind of to say that our naive idea, or my naive idea, wasn't too great, and we need to try and find a better metric to characterize the performance of our algorithms. Thankfully, a lot of smart computer scientists have thought very deeply, profoundly about this, and they have come up with a better runtime metric. This metric is known as Big O notation, and it's a really cool metric which actually addresses all three of these issues. So we're going to go through this step by step, but the high level idea is that instead of actually directly reporting time, Big O notation reports the number of actual operations that you had to perform in getting your output solution. Big O notation also characterizes the worst case performance of your algorithm. So it only considers your algorithm takes in the hardest possible scenario, the case in which the algorithm will take the longest time to run. Big O is also expressed as a function of input size. So kind of just going back to what I was saying at the end of the last slide, where if you only report a single value to try and quantify the performance of the algorithm in every situation possible, that just isn't going to work, right? We need some sort of functional metric that changes as the input changes. So to see this a bit more concretely, we'll start off with the notion of Big O reporting the number of operations. So the actual time it takes your code to run depends on a lot of things that are independent of your algorithm, for example, your hardware. So in Big O, instead of like using a clock to measure the amount of time it takes, which is kind of just in a sense looking at the number of operations, right? Because if you have more operations, it's going to take more time. In Big O, we just directly count the number of operations so that we can focus purely on the algorithm's efficiency independent of any hardware. So in the case of our linear search, right, each time that we checked an element in a list, we could consider that an operation. So in this example, right, our algorithm would take 5 operations. So the second key idea in Big O is that Big O notation characterizes the worst case performance. So dependent on how your input is structured, our algorithm could take more or less operations to solve. And we want to account for that in our metric. But of course, it becomes a lot more complicated if you're thinking about both best and worst case performance simultaneously. There are actually other metrics you could use that sort of tell you about the best case performance. But in reality, right, we're going to assume in the real world that we're dealing with the hardest data possible, which is probably true, right, for these hard applications like environmental science, climate change. So we want to know in the hardest case possible, how long would it take our algorithm to run? And so, for example, in this case of linear search, right, as I indicated, in the case that dog was the first item in our list, we would only have to perform one operation. Whereas in the case that dog was the last item in the list, we would have to perform 6 operations. And so Big O notation really only cares about characterizing the performance for this input. So this is the worst case scenario. And actually, this here is the best case scenario. And so Big O really just cares about this input. And so we'll assume that for any input length, when we use Big O notation to try and characterize our algorithm performance, we're only caring about the case of the hardest input. And then finally, to again address this notion of the fact that our input can change, right? We want our algorithm to be able to work on all possible inputs that we might see for a problem. And so Big O is actually a function. It gives us a function of input length. And so to make this a bit more concrete, in the case of our linear search algorithm, right, we said that in the worst case, we will need to check every list item. So this means that we'll need to perform as many operations as there are list items. So if we say that our input is of some arbitrary length n, then we will need to perform n operations. And if we're using Big O notation in the sort of mathematical sense, the way that we express this, the way that we represent or write it down, if we are on paper trying to say that for an input length of n, we need to perform n operations, is we write O of n. So if I'm just telling my friend and communicating it, I would say that linear search is O of n, and it's written like this. And now now we can actually see, right, why our algorithm was called linear search, right? I made a plot of the Big O as a function, right, of the number of animals in our list. And in the case of our algorithm that we designed, the linear search algorithm, right, we see that the number of operations increases proportional to the number of animals in our list, right? Because we said that if our list is, say, of length 1,000, we're only going to care about the hardest possible case, in which dog is the 1,000th element of our list, in which case we're going to have to check all 1,000 elements of our list before we get to dog. And as you increase the length of that list, you have to increase the number of operations you perform, but that increase is linear, right? It's governed by this. And so the final key aspect of Big O, right, is that it allows us to compare the performance of different algorithms. Using this Big O notation, we can actually say whether one algorithm is better or worse than another. And so on this slide here, I've kind of given a few concrete examples of different algorithm Big O's. And so And the plot on the right, you see the actual plots of each of these algorithms. And kind of the key thing to keep in mind, right, is that the smaller the function is, so the less quickly the function grows, the better, right? Because if the function grows quickly, that means we need to perform more operations, which ultimately is going to mean it takes more time. And we want our algorithm to run as fast as possible. So that's kind of what I'm indicating with this arrow here, right? More efficient algorithms have big O's that are smaller functions of input size. So the fastest possible algorithm you could have is a constant time algorithm, meaning that independent of the size of your input, your algorithm will essentially always take the same time to run up to some constant factor or multiplicative factor. The hardest possible scenario is if your algorithm has a factorial big O, but potentially more easy to visualize is the exponential case. So the amount of time your algorithm takes to run grows exponentially with the size of your input. And most problems that we consider to be truly intractable are ones that actually have these sorts of exponential runtimes. And so the final like kind of keynote I wanted to make about Big O in terms of this notion of comparison is because Big O, we're kind of trying to quantify algorithm performance generally. There might be kind of specifics of your hardware that maybe for certain input sizes will make it harder, but maybe as you increase, it'll slightly decrease small fluctuations that we don't really care about. What we care about is kind of in the infinite input size regime. As our data gets really large, how well does our algorithm perform sort of in general? And so if you think about this case of your input size getting really large, essentially what happens is the largest function in your big O function will dominate. So if you have like an exponential and you're just adding a constant term, the exponential is going to dominate, right? Because as soon as I get to 10,000, so 2 to the power of 10,000, if I add a 1 or not, that doesn't really make a difference. The key kind of bulk of the computation is being attributed to that 2 to the 10,000 or whatever it is. And so here I've given some examples of how in Big O, we kind of simplify different expressions. So we don't really care about multiplicative factors on our dominating term. So usually if you have like say O of 10, you'll just write O of 1. The key idea is that it's constant. Even if that constant isn't 1, it's not a big deal. In this case here, right, we had a linear and a constant term, but we actually just drop off that constant term, right? Because as soon as n is say 1 million, is there really a big difference between 2 million and 2,000,003? Not really. So we just care about the n term. And again, we can sort of ignore this multiplicative factor. Same thing here, right? The exponential term will dominate this n cubed term. So we just drop this term. Now, the base of our exponent is pretty important, right? Because if I have 3 to the n, for large n, that's much smaller than, say, for example, 10 to the n. So this base we usually keep, whatever it is. And then in this final example here, this is a bit of a tricky one, right? You might think that, oh, this is n to the 4th. And since 3,000 is such a big multiplicative factor, maybe this n cubed matters. But in reality, it doesn't, right? If n is 1 trillion, 1 trillion to the power of 4 is going to be a lot larger than 3,000 times 1 trillion cubed. Even though it might not seem like it, you can go and sort of run experiments on your own time on your computer to kind of verify that this logic is true. But the key thing I just wanted to point out on this slide is that in Big O, we kind of simplify things because this is all kind of thinking about the large term regime, how our algorithm will perform in really hard input cases. And with that, I wanted to give you guys some practice problems. So basically for each of these examples, just go through and try and think whether the big O on the left or on the right is bigger, smaller than, or equal to the other. And I'll give you guys maybe 2 minutes to work through these 3 examples, and then we'll go through solutions. All right, so hopefully you guys had a chance to think about all 6 of these. We'll go through solutions now. And again, kind of the key thing in Big O notation is making sure you kind of simplify your expression before you start trying to compare it to other things. So in this first case, problem 1, our Big O for this first term, right, just simplifies to O of n, linear, because n is the dominating term, so we can drop off the 1, and we don't care about the multiplicative factor. That being said, O of n is less than n cubed, right? N cubed is larger than n, so we'll say that if these were algorithms, right, this function here would be a slower or worse algorithm, right? Because it has a bigger Big O. Okay, so moving on to problem 2. This one's a bit tricky, right? Because you might intuitively think, well, this one is 10,000 times n plus 30, and this one is just 3 times n. So the one on the left is greater. But remember, in Big O, we don't really care about those multiplicative or constant factors. So these both will simplify to O of n. And these are actually both equal. At the end of the day, we just say these are both linear algorithms, because in that case, right, that n is 1 trillion. They're going to perform essentially the same. The big speed ups, right, come if we can decrease the kind of polynomial or the function of n itself. So this third case is a bit tricky. This is one that I sometimes have to check if I'm not super fresh on things. But if we go back a few slides, right, we see that log is actually slightly less than square root of n. So we say O of log n is less than O of square root of n. This one's a bit tricky though, so if you didn't get it, that's all right. So this fourth example, we have two exponentials, right? And the key in comparing these two is looking at the base, right? So if we were to take a specific value of n, let's say n equals 2, right? In this first case, we would get 36, whereas in this case, we would get 4. And so we would see that in the case of O of 6 to the n, both would scale exponentially, but the O of 6 to the n would scale more quickly than O of 2 to the n. So this one is greater. So this algorithm is a better or more efficient algorithm. The fifth case is actually very similar, just have different bases here. So using similar logic to the problem before, 10 to the n is greater than 3 to the n. And so this last one was kind of just meant to be a tricky question, if in the sense that you might think, okay, so this second term here only has e to the n, whereas this one has e to the n plus n squared plus n to the fifth power. So the one on the left must be greater, right? Well, remember, our big O rule is that we only care about the dominating term. Oops. So we're actually going to ignore both of these terms, because if we have n equals to 1 trillion, this exponential term is going to dominate so much more than either of those smaller terms that essentially they're negligible. And then again, remember, we drop multiplicative factors. So this one here on the left just simplifies to O to the e to the n. And so actually it turns out that these two are equal, and we say that both algorithms are exponential. So hopefully that makes sense. If you're still a bit stuck or confused, you'll see more concrete examples of this in lab and on your homework.
Fran, could I ask a quick question that's coming up in the chat? So how is example number 2 different from 4 and 5? Because it seems like in 2, we said that they're the same order, but in 4 and 5, even though they're all exponential, we are still saying that one is better than the other.
Right. That's a great question. So they are both exponential, but in exponentials, you actually kind of get a bit of a spectrum. So you could say they're equal in the sense that both are exponential, but in exponential growth, this base term actually makes a big difference. So people tend to say that if you have a bigger base, it is exponentially worse. This is kind of a nuance though. And for our general purposes, I guess we will be saying that they are equal to some extent. We classify them as exponential algorithms. But if you get a bit deeper into it, people might say that it is greater just because, right, as we saw here in this specific example of n equal to 2, right, 36 is already quite a bit bigger than 4. So if we were to have n equal to 10 or whatever, it would already be a way, way bigger number. Great question, though. It's a bit of a nuance, and you don't have to worry about these nuances for the purposes of what we're doing today. We're actually going to be looking at algorithms that achieve pretty big speed ups where you're moving from like exponential to linear or constant times. But thanks for pointing that out, Akshay. And so just for the sake of time, I'll kind of move on to, I think what's our final discussion point with Big O, which is really this notion of actually improving algorithm Big O. So now that we have a way to go about comparing algorithms, we can start to think about, okay, I have an algorithm and I can quantify its performance or efficiency. How can I actually go about improving my algorithm so as to make my algorithm faster, thus reduce its big O function? And so going back to our example of linear search, now I'm going to kind of modify the problem. Instead of saying we're searching through a list of animals, we'll actually be searching through a list of numbers. With one key insight here, right? Our list of numbers is going to be sorted in this case. So we know that someone went beforehand and made sure that the smallest item was put first, the largest item was put at the end of the list, and now we're doing a search in a sort of structured regime. In this case, we can ask, is there a more efficient algorithm than linear search for, say, finding the number 5? So let's work through our example, right? Linear search, in this case, we would have to check every single item in the list to get to 5, and 6, since there are 6 elements in the list, this corresponds to 6 operations. Now, if you take an algorithms class at some point, you'll probably end up learning about an algorithm known as binary search, which makes use of the structure in this data to actually improve the speed of your algorithm. So the way that binary search works at a high level is we're basically at every step going to split our list in half. So we're looking for the number 5, right? So what we're going to start by doing is splitting our data in half, going to the middle of the list and saying, okay, is 5 less than or greater than the current item in the list? And so we see that we're between 2 and 3, and we know that 5, right, is greater than 2, 3. So since we know that the data is sorted, we can just throw away this half of the list. So now we've reduced our list length in half. And so now we come to the number 4 and we ask, is 5 greater than or less than 4? And we know that 5 is greater than 4. So that means that we can throw away, we can throw away this half of the list. And basically we just move to the right and we see that we're at 5. So we've actually managed to find the number 5 in 3 operations, simply by at every instant in time, instead of just looking kind of naively at every element in the list, using this fact, right, that we know that the list numbers are sorted. And so by leveraging the structure of our input, we were actually able to get a much faster runtime. It turns out if you characterize this and do some more advanced algorithm analysis, the runtime of this algorithm is O of log n instead of O of n. And I wanted to use this algorithm speedup to introduce kind of our last key bit of terminology we need to know before we start looking at quantum algorithms, which is the notion of speedup. So by kind of leveraging the notion that our input was sorted, we were able to cleverly come up with a better algorithm. And so we say that this algorithm offers a speed up to our original search algorithm. Binary search offers a quadratic, or logarithmic speed up to linear search. And so later on, when we talk about quantum algorithms, actually, that's my next slide here, we'll also be using big O to characterize their efficiency. And really our goal in designing a good quantum algorithm is to achieve a big O, which is smaller than that of any classical algorithm for the same task. So essentially, when we write out our big O, we want our big O of our quantum algorithm to be smaller than our big O of our classical algorithm. And as I kind of hinted at the start of the lecture today, there's a lot of important problems which have very large classical big O's. This includes problems like the traveling salesman, where you're trying to find an optimal sort of plane scheduling between a bunch of different cities with different costs. Optimization machine learning, where you're trying to find an optimal solution to a very complex problem. Quantum chemistry and simulation, where you're trying to simulate really complicated quantum systems, or protein folding, drug design, which has been in the news quite a bit recently because the Google AI team, just in classical machine learning, we're able to get a pretty good speed up improvement for this problem. But that's another problem which is very hard. But of course, we would like to know how proteins fold, because that could actually inform how we design new medical treatments, drugs, things like the coronavirus vaccine. And so basically, a lot of these problems that we can't solve today fully or as well as we would like to, because they have large classical big O's, we hope that we can design quantum algorithms that will give us such a big speed up, we'll actually be able to solve them within reasonable, useful times. And so the rest of today's talk now that we know what algorithms are and how we can characterize and compare them, we're going to be talking about the actual quantum algorithms landscape. So quantum algorithms that people have designed. And so I wanted to start off by defining what a quantum algorithm actually is, and sort of just ask you guys, this structure that I use to introduce the classical notion of an algorithm, right? Input, computation, output. It should look a bit familiar to something we've already seen in this class, right? And maybe it'll be a bit reminiscent of sort of our state and measurement discussion we had a few weeks ago when we were first introducing the notion of the quantum circuit model. In fact, kind of this whole time we've, to some extent, been talking about quantum algorithms, but quantum algorithms in disguise. It turns out that all quantum algorithms actually boil down to quantum circuits, right? Because we have an input, a computation, and an output. But that's not to say that every quantum circuit is necessarily a useful quantum algorithm. Like if you just go in Qiskit or on the IBM Quantum Experience and throw together randomly a bunch of gates, sure, you could call that an algorithm, but if it's not solving a useful problem, no one's really going to care. So kind of the key idea in quantum algorithm design is trying to design a quantum circuit which actually performs a useful computation and does it well. Well in the sense of those two metrics, right? Accuracy and efficiency. So furthering this notion of good quantum algorithms, we believe there's a lot of potential for using quantum computers to get big computational advantages over classical systems. But this requires clever algorithm design. And quantum algorithms need to strategically leverage our three quantum resources we've talked time and time again about in the class: superposition, entanglement, and quantum interference, which are kind of the three resources, right, that we said quantum computers have, which classical computers don't have, and thus allow quantum computers to get some sort of quantum advantage. So now let's discuss what exactly this term quantum advantage means. Well, quantum advantage is just the notion or a demonstration that a quantum device can solve a problem significantly faster than any classical device. Traditionally, this concept is known as quantum supremacy. In recent years, people have kind of been moving away from it just because of some bad connotations coming with the word supremacy. But there was a pretty exciting result actually not too long ago, in October 2019, in which Google AI Quantum achieved the first ever experimental demonstration of quantum advantage. In using a sort of small, noisy quantum device, which only had 53 qubits, they were able to calculate a result in a few minutes that would take the world's largest supercomputer several days to solve, which is pretty wild, right? This is not a particularly great quantum chip in the sense that in the future we'll have quantum chips which have tens of thousands of qubits and are essentially noiseless. But with a small, noisy device, they were able to outperform the world's largest supercomputer, which is really incredible. Now, the problem they actually solved wasn't too particularly interesting, but the fact that they were able to do it got a lot of people really excited, and made people hopeful for the future of the field. One other interesting thing to note, right, is the paper that came out has a huge author list. And so this definitely was not an easy feat. It took a team of really talented scientists and engineers several years to achieve. But it was one of the great feats of the field, especially in the experimental domain until now. And so the rest of the class, we're going to be focused on essentially a few of the core quantum algorithms which offer big computational advantages. So algorithms that people have developed over time, which solve problems much better, much faster than classical computers. These algorithms, though, are a bit complicated, so we're not going to have time today to really teach you everything there is to know about these algorithms, but we're going to introduce them and focus on a key technical takeaway from each of the algorithms that kind of is what makes them interesting or different from a classical algorithm. And with that, I think we could take a quick break. I'd say maybe just a 5-minute break to make sure we have time for that programming review at the end. So let's come back at 3:08 p.m. EST. All right, everyone. Sorry about the short break, but I just want to try and make sure we finish up on time so that Akshay can start his programming review on time. Also, for the sake of time, I won't answer any questions now. Maybe if we have some time at the end, I'll get back to them. But let's get into quantum algorithms. And so for the remainder of lecture today, I'll be presenting sort of 4 key algorithms, and I'll actually be following the sort of timeline in which they were invented or developed. So the first algorithm we're going to talk about today is the Deutsch-Jozsa algorithm. So the Deutsch-Jozsa algorithm was invented by David Deutsch and Richard Jozsa in 1992. You might ask, what problem does Deutsch-Jozsa solve? Well, it turns out that much like the Google quantum advantage result, the Deutsch-Jozsa algorithm doesn't actually solve any useful problem. For all intents and purposes, it solves a toy problem. It's basically determining whether a function is constant or balanced. For the sake of time, I won't get into that, and you'll actually learn more about it in the lab. But the reason why we care about the Deutsch-Jozsa algorithm is that it was the first theoretical demonstration of quantum advantage. So like this Google experiment was the first sort of experimental demonstration of quantum advantage, this algorithm was really the first time that people were able to show you could create a quantum advantage, which theoretically will always outperform the best classical algorithm. And in fact, the Deutsch-Jozsa algorithm offers a huge speed up to classical algorithms. For the problem that they're trying to solve, the best classical algorithm is has an exponential big O, whereas the Deutsch-Jozsa algorithm is a constant time algorithm. That is huge, going from exponential to constant time, and we refer to that speed up as an exponential speed up. Now, in terms of how the Deutsch-Jozsa algorithm actually achieves that speed up, is through its use of an oracle. Now, I had never heard of an oracle actually until I was first introduced to the Deutsch-Jozsa algorithm. So I just want to take a few minutes to introduce you guys to this concept because it's a bit weird. The notion of an oracle comes from complexity theory, so hardcore classical computer science. And it has all sorts of definitions. A lot of time people like to just call it a black box. But when I think about an oracle, I like to kind of think of a sort of magical, all-knowing genie. So you can really think of an oracle as a genie that kind of grants you a computational wish for free. And there are 2 different types of wishes which an oracle genie can grant. The first is you could go to the genie with a decision problem. So given a problem, which you can specify by an input, like a bit string, the genie will tell you whether or not the answer to your decision problem is yes or no, 1 or 0. The second type of problem you could approach your genie with is a function problem. So you have some input, x, which you can represent as a bit string, and you can go to the genie and ask it to calculate an output to some function, f, which you might actually not even know what it is, but you know that f is really important for something you want to do, and you leverage this genie's sort of all-knowing power and computational ability. And kind of the key idea with the notion of an oracle is that you're really giving this genie an input. He's going to perform some computation, and you don't have any idea what this computation is, how he's doing it, how he thinks about it. It is really a black box to you, but he's always going to return the correct output, and he's actually going to do it instantaneously. So I'll also put that here. I think I'm spelling this right, but you guys get the idea. And so If we look at the actual quantum circuit of the Deutsch-Jose algorithm, we see that it's fairly small. You have some inputs, you apply Hadamard to put those inputs in a superposition. The key idea is you have inputs to a function, and you're basically putting them in a uniform superposition so that you can simultaneously test every single input at once, rather than in a standard classical algorithm, right? You would have to go one by one and test all those inputs. Then you have an oracle, which is represented by this box here circled in purple, which is, right, your genie who performs your function for you, or calculates your function for you instantaneously, does it somehow magically. And then from there, you kind of get a result. You just perform a single measurement and it tells you whether or not your function has a certain property. Now, this is all very abstract, high level, and you'll be seeing the Deutsch-Jose algorithm much more in lab this week and learn concretely how it works. But the key idea really here is that the Deutsch-Jose algorithm was the first demonstration of quantum advantage, a huge exponential speedup, and it makes use of this notion of an oracle to get that speedup by putting an oracle in a quantum circuit. So our next big algorithm, which we've actually mentioned a few times throughout the class, is Shor's algorithm. And that was invented in 1994. So Peter Shor developed Shor's algorithm in 1994, but Shor's algorithm actually makes use of a more fundamental algorithm known as the quantum Fourier transform, which was also invented in 1994 by a man named Don Coppersmith. And so as we've hinted at throughout the class, right, Shor's algorithm was kind of one of the big things that got people excited about quantum computing, because it enables you to factor large integers very efficiently by boiling it down to this problem known as period finding. But ultimately, the main reason why we care about it, right, is that RSA encryption, our main crypto system in use today, is only secure under the assumption that large integers are hard to factor. So if you could actually implement Shor's algorithm and run it and efficiently factor large numbers, then you could essentially break all of modern cryptography, hack into anyone's emails, companies, whatever it may be. So this has huge societal implications. And basically, the best kind of classical algorithm for factorization to date has a runtime that looks something like this, O of n to the 1.9. It simplifies to that. We'll see the actual runtime in a few slides. Whereas Shor's algorithm brings it down to a logarithmic runtime. And so we say that Shor's algorithm gives us a super polynomial speedup. Now, in terms of kind of key technical takeaways, kind of the key thing I want you guys to remember is that Shor's algorithm uses the quantum Fourier transform. We'll now spend the next few slides kind of building intuition as to what exactly the quantum Fourier transform is and why it's applicable to this notion of factoring large integers. So in quantum Fourier transform, probably the one word that you guys wouldn't be familiar with is the word Fourier. Fourier is actually the name of a very famous French mathematician, Joseph Fourier, who in 1822 came up with this incredibly smart, useful result that had huge implications for mathematics, science, and engineering. And basically, all he did was show that any function can be represented or extremely well approximated by a linear combination of trigonometric functions with varying frequencies. So basically, by taking a linear combination, for example, of cosines of varying frequencies, like you can see in this picture here, you can actually represent almost any function you can think of. You might have to add more cosines if you have a really complicated function, but at the end of the day, you can. And that's like a pretty significant and mind-blowing result. And And this idea that you can decompose functions in terms of these trigonometric functions with frequencies is known as Fourier analysis. Now, this work on Fourier analysis then led him to develop one of the most important equations in science and engineering, a tool known as the Fourier transform. Now, what the Fourier transform does is it provides a mapping from the time domain, so the usual space our function will lie in, to the frequency domain. And the reason why this is important is by moving to the frequency domain, you basically can see the coefficients of the different trig functions in your original linear combination. And it basically tells you how strong certain frequencies are in our signal. It allows us to figure out which frequencies are the most important in our function. And kind of just a fun fact to relate the notion of the Fourier transform to quantum mechanics that you guys saw earlier, it turns out that the momentum position relationship that Amir talked about when he was talking about the Heisenberg uncertainty principle and all of that, mathematically, that's all being governed actually by the Fourier transform. It all kind of relates back to this notion of wave-particle duality, right? Because your waves have frequencies, and things like that. That's a bit about, beyond the scope of this class, but kind of just to give you some motivation as to why the Fourier transform is applicable, just generally speaking. Now, the quantum Fourier transform, what that was, what Don Coppersmith invented in 1994, was literally just a quantum circuit, which kind of implements this Fourier transform by essentially encoding frequency information into the phase of our quantum states. So we have an input to our quantum Fourier transform circuit. And essentially what it'll do is it'll take the frequencies encoded by those input quantum states and map them into the phases of a resulting superposition that will come out of our quantum Fourier transform. I know this probably sounds a bit abstract and complex, and definitely not expecting you guys to come out of this class knowing what the quantum Fourier transform is. Shor's algorithm and the quantum Fourier transform are probably two of the hardest algorithms you could study or learn about in a quantum computing class. But we're just trying to build some intuition for what's going on here. And at the end of the day, both the Fourier transform and quantum Fourier transform are essentially just performing a change of basis. In the case of the classical Fourier transform, you're transforming from the time domain or a set of time bases to the frequency domain, which is governed by a set of frequency bases. And so it turns out actually that you guys have already seen the quantum Fourier transform in action, because for a single qubit, the Hadamard is actually the quantum Fourier transform of a single qubit input. So if we give an input to the Hadamard, right, that's in the Z basis, 0 or 1, it performs a mapping, right, to the X basis, because our output states will be the plus or minus state, which are uniform superpositions, right, of 0 and 1. So that's a fun fact. You guys have already seen the quantum Fourier transform in action. And kind of the key intuition between Shor's algorithm is that it turns out if you take very advanced sort of number theory classes, you'll learn about this more concretely, but just believe me when I say it, the problem of integer factorization actually is a problem of period finding. So finding periods, which the period, right, of sinusoid is just 1 over its frequency. So ultimately, the problem of integer factorization is about figuring things out about the frequencies at hand. And as we saw, right, the Fourier transform, quantum Fourier transform are tools that enable us to gain information about frequency. And so Shor's algorithm makes use of a quantum subroutine known as phase estimation that basically leverages the quantum Fourier transform to get this information about periodicity, which then is used for integer factorization. So a lot of steps of abstraction there, but that's kind of the workflow in Shor's algorithm. Now, we spent a lot of time at the beginning of class kind of talking about big O notation, right? And I just wanted to emphasize sort of how much of a speed up Shor's algorithm offers by boiling it down to the big O notation. So I said before, right, that Shor's algorithm gives a super polynomial quantum speed up for factoring integers. But if you just look at, so here and here, I've actually reported the true big O notation for the best classical algorithm and Shor's algorithm for this problem of integer factorization, but those are pretty nonsensical if you're just looking at them. So I approximated them to these two functions, which even then, if you look at them, right, it's pretty hard to compare them just by looking at the functions, how they scale as a function of input size. So what I did over here was I basically made plots of the actual functions and how they compare. And so in between these two red dotted lines is inputs, which correspond to the RSA key lengths used today for encryption. So these are the type, this is the input regime, really, in which you need to be able to factor large numbers to break modern cryptographic systems. And if you see, right, this classical line plotted in blue, it takes a huge computational complexity. I'm plotting on a log scale here. So I don't know, if I had an RSA key of like roughly 1,000 bits, my computational complexity would be 10 to the power of 31. I don't think I can even like visualize how large of a number that is. Meanwhile, if I had a computer which was large, a quantum computer which was large enough on Shor's algorithm, I could solve that in just 10 to the 7 operations. So Shor's algorithm offers a really huge speed up for being able to actually hack into RSA encrypted systems, which is really, really cool and actually makes systems that we use today hackable in finite amounts of time, which I guess means that we as a society need to really think forward about implementing post-quantum cryptography schemes, right, which we talked about a few lectures ago, to make sure we are secure from these attacks. So hopefully that helps you visualize the significance really of Shor's algorithm and the speed up it offers. Now, the next kind of big algorithm that we're covering is Grover search, which was invented in 1996 by a man named Love Grover. And the key problem he was trying to solve was actually the search problem that we looked at before. However, this was search assuming that our data has absolutely no structure. So binary search wouldn't work in this case. Yeah, just trying to see if we can come up with an improvement over linear search. It turns out that if you assume your data has no structure, linear search is really the best you can do to guarantee you'll get the correct output every time. But it turns out, and Grover cleverly came up with a quantum algorithm that offers what's known as a quadratic speedup for the problem of search. So going from O of n to O of root n. And kind of the key idea behind Grover's algorithm is this concept of amplitude amplification, which I think is a really beautiful idea. And Professor James Whitfield, I think, was talking about it a bit for those of you who could join before a lecture for his discussion. But it has a really nice visual interpretation. So I just wanted to walk through quickly what the high level idea is what the high level idea of amplitude amplification is. So Grover, he came up with this search algorithm, and a few years later, people realized that the key idea that enabled this search algorithm to get a speed up was actually a technique that then people could apply to a bunch of other problems. And this technique was formalized as amplitude amplification. And so the key idea here is that through clever circuit design, you can actually amplify the probability of measuring a bit string corresponding to the index of the item you're looking for. So if our goal is given a list that looks like this, we're trying to find some winner state W. What we'll do in Grover's algorithm is we will start off by applying Hadamard's, basically to create a uniform superposition over all of the possible bit strings, which correspond to all the different possible indices, because we have no idea where our item is in the list. Now, we'll design an oracle, right, our genie that we can go to who can perform any kind of computation somewhat magically and instantaneously. And this oracle will flip the sign of the amplitude of the probability of W's index. So basically just applying a negative phase. And then the idea of amplitude amplification is that once you flip this negative phase, if you can find a way to then perform basically a reflection around the average of all the amplitudes, well, your amplitude that was here is going to go all the way up here, whereas these amplitudes, right, and getting reflected, they're going to be brought down here. And so basically all it's doing is it's boosting the amplitude, or which then corresponds, right, to the probability of measuring your winner state relative to the others. And basically what Grover did was he found the exact number of times you need to go through this procedure to maximally kind of amplify your winner state to guarantee that you'll measure the right state if you run the algorithm a few times. So that was kind of a crash course of Grover's. I know we're going through things pretty quickly, but hopefully these ideas are all making sense and you guys are getting a sense of that quantum landscape. So just because we're running out of time, I will go through kind of the last group of algorithms, which are near-term hybrid algorithms. And I want to just dissect what I mean when I say this. So by near term, I mean that we want algorithms which make use of the small and noisy quantum devices that we will have access to in the near term. So we're starting to see, right, companies like Google, IBM, they already have chips with on the order of 50-ish noisy qubits. And that will only increase and the amount of noise will decrease in the years to come. But we don't want to wait, right, until we have quantum computers with tens of thousands of qubits, which are all noiseless, to actually be able to run useful algorithms. Hybrid is this notion that since quantum devices are actually limited, but we already have classical computers today, which are extremely powerful and work very well, let's have them kind of work together or in unison so that the classical devices can kind of improve the performance of the quantum devices and have them work hand in hand. And so there's been a lot of work in recent years on developing near-term hybrid quantum algorithms, primarily focused on these variational quantum circuits. And so the key idea in a variational quantum circuit is that you have some quantum circuit, like the ones we've seen in this class, where the components of those quantum circuit, right, correspond to rotation. So in the single qubit case, it's a rotation in the Bloch sphere. And what we can do is we can parameterize the angles of rotation, so leave it as a free variable. And a classical computer can then be used to optimize the values of these parameters for the specific output we're trying to achieve. So we'll run the quantum circuit, see what output it gives, feed that into a classical algorithm that will then tell us how to update the parameters of our quantum algorithm to then hopefully improve its performance so that the next time we run that quantum circuit, we'll get a better output and so forth. And so Amir will be talking about this towards the end of the class in more depth, but I just wanted to go through some current use cases for these variational and near-term algorithms that people are actually playing with today. So kind of going back to Richard Feynman's original notion of simulating quantum on quantum. One kind of neat thing to note, right, even just in sort of designing quantum chips is the fact that you can actually think of the hardware or your quantum device, the bits in it, while they do correspond to like bits on a classical computer, you could think of the qubits also as being artificial atoms, so macroscopic atoms. When I interviewed Professor Will Oliver for an article that I was writing on quantum computing at MIT, he liked to say it was an atom composed of an Avogadro's number of actual atoms. And the really cool thing here, right, is that if you start to think of your bits as artificial atoms, well, what happens when you put atoms together, right? Putting atoms together give you molecules. And so if you wanted to say simulate how a molecule would maybe evolve over time or interact with other molecules, the way that you could go and implement this on a quantum device, right, is you say, okay, maybe this qubit corresponds to an oxygen atom and this corresponds to a hydrogen atom. And then you'll design a quantum circuit or let your system evolve in such a way to model the actual types of interactions that you want to study for a true molecule. And so you're kind of using your quantum computer, this like computer chip, as a physical simulator of real quantum properties. And so this, you can imagine, right, is a lot faster than on a classical computer where you have to go and kind of encode all of the logic, write up code, which might probably be wrong or noisy. So getting all sorts of advantages there for quantum simulation. And then we can apply this idea back to the problem of environmental science, actually, that we were talking about at the beginning of class. So people have already worked hard to develop sort of hybrid quantum algorithms. One specific one that comes to mind is the variational quantum eigensolver to sort of simulate molecules and chemistry and solve for those important properties that might be useful in developing new materials in the case of environmental science or things like that. And so the variational quantum eigensolver algorithm is actually already being used to solve several problems in quantum chemistry and material science, such as finding the ground state energy of a molecular system. This isn't the only way to do that. People are playing with all sorts of algorithms of this type. But there's a lot of cool work going on in quantum simulation using quantum circuits, which being run on small, noisy quantum devices today. Now, I just wanted to conclude today's lecture by talking about an application to something that I personally am really excited about. I think I told you guys at the start of the semester, right, that following my time here in the UK, I will be starting a PhD in quantum machine learning. And so I wanted to kind of tell you guys, share with you guys why I'm so excited about that through actually the specific example that got me excited about the idea of quantum machine learning a few years ago. It made me decide to commit to a PhD in it. So there are a lot of interesting aspects to machine learning, but one common problem in machine learning is this problem of classification. And if I were to boil classification in a nutshell, I would say basically you have two, let's say you have an example, you have a set of images of dogs and cats, and you want your computer somehow to tell you, given a new image, whether it is a dog or a cat. If maybe you could map it onto a 2D plane, you would see that all of the dogs lie on one side of the plane, all the cats lie on the other. You could kind of just draw a classification line or boundary and just say, okay, if I get a new image and its corresponding data point falls on the blue side of the boundary, it's a cat. If it falls on the right side, it's a dog. And in this case, which is really simple, right, the data has a very nice structure to it, we see that it can be separated with a straight line. And we say that this ability to be separated by a straight line means that the data is linearly separable. Now, it turns out that typically real world data is not actually linear separable. And it's a really, really hard problem often to find a function which would perform classification. You could imagine if your data was not linearly separable, your classification boundary would have to look something like this. And maybe there would be regions in which it doesn't work and so forth. And so one idea that people came up with to address this issue is the notion of a feature mapping. Basically, a feature mapping is a function that you apply to your data to transform it to some higher dimensional space in which it does become linearly separable. So I just gave a simple example here. You have data of this form, right, which was not linearly separable because we need to draw kind of two independent lines to classify the data. If it was linearly separable, for example, if this was blue and this was red, this was red, we could just draw a single line and that would be linearly separable. But in this case here, it's not linearly separable. So what do? We apply this function phi, which takes basically the x values of our data and projects it into a two-dimensional space where the x-axis is x and the y-axis is actually the original x value squared. And so that takes 1 to the 0.11, but it takes 2 to the 0.24 and so forth. And we see in this new higher dimensional space, our data is actually linearly separable. So this is all just a crash course in classical machine learning ideas. But what got me super excited about the prospects of quantum machine learning was this paper I discovered back when I was in undergrad called Supervised Learning with Quantum Enhanced Feature Spaces, where a bunch of really smart researchers at IBM and MIT were able to come up with a variational quantum algorithm that found a way to learn powerful feature mappings simply by kind of projecting things into the block sphere and using like this probabilistic discriminator. The actual details of it are a bit technical, but in reality, they were able to use a quantum algorithm to learn something much more powerful than what could be done classically. And I thought that was super cool. And I think there's a lot of similar potential for quantum algorithms in the years to come. So here's kind of our nice summary slide of the different algorithms we covered today. I could go on and talk about algorithms even more. And you will continue to see algorithms in the week to come. But hopefully this gives you guys a sort of idea of all of the different types of algorithms. While there are many other quantum algorithms, most of them kind of are very similar to these four algorithms, maybe taking key ideas like amplitude amplification or the notion of an oracle, the quantum Fourier transform, and applying them to slightly different problems or different applications. But most tend to have similar structure to one of these four. And with that, this is my last lecture. So I just wanted to say thanks to all of you guys for what's been an awesome year. You really made coronavirus and dealing with the pandemic a lot more fun. It was super great teaching you all. I really hope that you guys never stop learning and having fun while you do so. That's the most important part, right? Make sure you're having fun along the way. I can't wait to see where your quantum journeys take you and all the great things that you guys are going to achieve in the years to come. Hopefully some of you will end up doing quantum computing in the long term, but even if you don't, I hope you've gained valuable skills that will help you down the line in whatever STEM or maybe not even STEM career you end up pursuing. So thank you guys. And I guess I will pass it over to Akshay now for programming review.
Thanks, Fran. And you can see in both the chat and the Q&A how much everyone loves you.
Thanks, Akshay. Thanks, everyone. It's been a lot of fun.
All right. Rachel, should I just transition into the programming review directly, or did we want to pause for any announcements?
No, go right ahead if you want to just tee up kind of what you'll cover so people can decide if they want to stay in some of the rationale for why we're doing this review.
Yep. So I'll be doing some very basic Python to concepts that we discussed briefly in semester 1, just as a review for everyone in case you're still having some questions about like just the fundamentals of Python coding. So I'll be talking about things like variables, if statements, functions, loops. And so if you feel comfortable implementing those ideas, then feel free to drop out of the lecture. But if you still have questions about those Python fundamentals, maybe when you see them in the lab notebooks or the homebook notebooks, then stick around and we can do a quick review of them. So if you want, you can follow along with what I'm doing on Replit. I'll be showing like a series of problems which you can code for yourself. But if not, you can just look at what I'm doing and you can ask questions and discuss. Yeah, so can you see my screen, Rachel?
Yep, this is perfect.
Cool. Okay, so yeah, I just made a quick list of what we'll discuss in this review. I'm aiming for something like 20 minutes to 30 minutes, so I might go a little bit over. Sorry about that. So once again, if you have questions about these basic Python concepts, then stick around and we can have a good discussion on them. But if not, feel free to drop out. So yeah, I'll be talking about variables, lists, if statements, for loops, and then finally functions. These are all ideas that we've been seeing repeatedly whenever we code using Qiskit. And so this is meant to be just a quick review so that you can get more comfortable with everything that we do in the labs and homeworks. So I'll give people maybe 30 seconds if you want to fire up your applet to follow along, and then I'll begin. To answer a couple of the questions, this review is not yet available on Canvas. I will post the completed notebook on Canvas afterwards. And we are just reviewing Python, not Qiskit, in this session. Okay, so I'm going to begin. And Rachel, maybe you can pass along some questions to me as they come up in the chat or the Q&A. So let me begin by just talking about variables, right, which are what we use to store different data values in Python. And there isn't a specific command, there isn't a specific way that you like declare a variable in Python. You just like give it a value and that creates your variable. And the way that you give it a value is just by using the equals sign. So if you just say variable equals some value, that is just going to generate your variable for you. So I have a quick question, which you guys can code along with me. So I want you to create two variables. That should be a 2, not a 3. Sorry. So I want you to create two variables, one called name, which just stores your name, and another one called bit, which just stores either a 0 or a 1. You can pick either a 0 or a 1. Okay. And then I want you to just print the sentence. The value of your name's bit is, and then print the value of the bit. So that's the coding task that I want you guys to try to do. So to repeat, I just want you to create a variable called name, which stores your name in it. Then I want you to create another variable called bit, which just stores either a 0 or a 1. You can pick your favorite one. And then just print the sentence. The value of your name's bit is, and then print the bit value. So I'll pause for maybe a minute to let you guys figure this out. If you want, you can send me your code through the Q&A. You can try the coding on Replit. If you're using like PyCharm or Jupyter for coding, you can also use that. Up to you. Or you can just follow along with what I'm doing right now and ask your questions. All right, so I'll give you 30 more seconds to try this out. So 2 variables, name and bit, and then print the sentence that's on the screen. All right, let's try this out. So I want to create these 2 variables. So what I'm going to do first is I'm just going to say name equals Akshay. The reason I need to include that Akshay inside double quotes is just because Akshay is a word. And usually in Python, when you want to store a word inside a variable, you have to enclose it in double quotes. These words in Python are called strings. So Akshay is stored as a string. And then I can say bit equals 0. I would just like to use 0 here. You can use your favorite bit. Okay. And then to print, we just use print the value of, and then if you want to print more than one thing, the way we do that is we just use plus. So plus name so now that's, and then in quotes, bit is, and then once again, I'm going to add a plus, and then I'm going to say bit. Okay. Let's run that and see what happens. Okay, so I got an error. Can anyone tell me, like, why didn't this work? Why did this not work? You can answer in the Q&A. Why did this not work? Oh, yeah, thank you for that suggestion. I'm just enlarging my screen here. Rachel, did that actually zoom in? I just want to check.
Yes, it did.
Okay, cool. Yep, so a lot of you are saying that the problem here is that the bit, this bit that I'm printing, right, it's a number. And in Python, you can't just use this format to print strings and numbers at the same time. So what I need to do is I need to convert my bit into a string. And so you do that by just using this str, and then you put in the bit in brackets. And if I then print it, and then it prints the value of Akshay's bit is 0. So this is how we create and we can print variables. Any questions on this before we move on? Next, I'll be talking about lists. So any questions on variables, on printing and things like this? Rahul, I will be sharing this notebook after the lecture. We'll put it up on Canvas. Does it understand space? Yes, it does. So you'll notice that I put a space at the end of off. So yes, it does. Okay, I'm not seeing any questions related to this. I'm going to move on to lists. So lists are what we use to store multiple values at the same time. So you will have noticed that in those variables I declared up in my code, I could just store like one bit or one name. We use lists to store multiple numbers or multiple names in the same variable. The way we make lists is by using square brackets. And you have seen lists already, right? We saw lists last week when we were doing quantum key distribution. We were storing the qubits that Alice is sending Bob as a list. So we have seen lists already. And the way that you can access any one element in a list is you use its index number. And indices in Python begin with 0. So the first element of the list is index 0. The second one is index 1. and so on. So here's a second question, which you guys can again start coding in Replit or whatever you're using. I want you to create a list, which is called myList, and store the names of all the quantum gates you can think of. We've been spending a lot of time now looking at the different quantum gates. So I want you to create a list called myList and just store all the different quantum gates that you can think of inside that list. And then once you've created that list and stored all the different gates, I would like you to print the whole list, the length of the list, how many elements there are in the list. And finally, I want you to print the fifth element of this list. So if you start counting from the start of the list, right, you have one first element, second, third, fourth, and I want you to print the fifth one. So I'll give you guys maybe a minute and then we'll code together. And as usual, you can just keep on sending me any questions you might have in the Q&A. So yeah, just try creating this list. You'll use square brackets to create it. And then try printing the whole list, then the length of that list, and finally try printing the fifth element of that list. Pablo, I'm hoping to finish the review in another 15 to 20 minutes, but it is going to be recorded, so you can check out the recording later. Okay, maybe 20 more seconds, and then we'll start coding. I like, Hemant, I like your list. Yeah, you guys can feel free to send me your code in the Q&A. Okay, so let's try coding this. I'm going to create a variable called myList, and I'm going to say that is equal to square brackets. We use square brackets to create lists. And then let's see, X gate, Y gate, Z gate, H gate, C naught gate. What else? RX gate, thank you, Javier, for that suggestion. RX gate, right? We can keep going. I'm just going to end my list here, but obviously we can keep on including more and more gates here. So that's the list. I included each of them in quotes because once again, these are all words, right? So I would just like to have them in quotes. Okay, then I'm going to print the whole list. So just print my list, and that's going to print my whole list. Then I'm going to say print, and now I want to find the length of this list, and the function we use for that is len, L-E-N, and then my list. And that's going to tell me how many entries there are in my list. And then finally, print my list. And then to specify a specific term, we use square brackets, and then we can enter the index of that term. And so here I want the fifth element. But remember, these indices start at 0. And so I'm going to print my list 4, which is going to print the fifth element. So let's run that. And so we get that we printed out the entire list. This tells me that the length of my list is 6. So let's just double check. 1, 2, 3, 4, 5, 6. Yep. And then finally, this is telling me that the fifth element is C naught. So let's just check that. First, second, third, fourth, fifth. So indeed, the fifth element is C naught. Okay, any questions on lists? Just basic handling of lists. How do you create them? How do you print different elements before we move on? Amol, I'd recommend reviewing the NumPy labs that we did at the beginning of the semester, because I think that in those labs we discussed matrix multiplications as well as how do you define vectors, etc. So I would recommend reviewing those labs. Okay, so I'm not seeing any questions. So I'm going to move on. And now we're going to be talking about control flows, loops, and if statements. So once you have defined these variables or lists, right, often it's very useful to compare them with each other to make decisions based on if one thing is bigger than or smaller than another thing. So that's what we mean by control. You can control what your code is doing based on some comparison that you make. And the way you make comparisons in Python is you can make different kinds of comparisons by using these different operators. So equals, you just use the double equals operator. Not equals, you use exclamation mark equals. Less than equal to, greater than equal to. So those are pretty self-explanatory and why those look the way they do. As a quick question, can someone in the Q&A tell me, why don't we use A equals B for the equals comparison? If you want to compare if A and B are equal, why don't we just say A equals B for that check? Why is that like a double equal sign here? Yeah, exactly. So a lot of you are saying in the chat that if you just do A equals B, right, what that's going to do is it's going to give A the value of B. It's not going to compare them. So to explicitly say that you're comparing them, we are using these two equal signs. Okay, so let's use our knowledge of these comparisons to now talk about how do you use them to make decisions in your code. Okay, so that's what we mean by an if statement. You can use if statements to use these comparisons and make decisions. So an if statement is going to perform an action if only if a certain condition is true. If it's false, then whatever action you've told your code to perform will not be performed. And we just use the keyword if to write if statements. And you can also use if statements to test multiple conditions sequentially, one after the other. And we use this construct of if, else if, or elif, and we can add another else if, and so on, and finally an else. And one really important thing to remember here is that the indentation must be correct. So in other programming languages that you guys might have seen, um, other languages use like parentheses or something to separate different bits of code. In Python, we use indentation. So if you want to include some code inside an if statement, it must be indented. And I'll show you what you mean when we do. I'll show you what I mean when I do some coding in just a moment. So here's a question that I want you guys to try to implement using an if statement. So I want you to create two variables, A and B, and they both store a bit value. So both A and B can store either 0 or 1. So for example, A and B could be the results of a classical measurement on a 2-qubit quantum circuit, right? When you measure a 2-qubit quantum circuit, in both of the bits, you're going to get either a 0 or a 1. And then I want you to print A is greater than B if A is greater than B. I want you to print A is equal to B if A is equal to B. And I want you to print A is less than B if A is less than B. So here's here's an example of where an if statement can be really useful. Okay, so I'll give you guys a minute or maybe 2 minutes to think about this, and then we'll start coding. And once again, you can just send me your code in the Q&A, as well as any questions that you have. So Claire asks, do we need end commands? So I'm assuming you mean, do we need to write an end when the if statement is done? So it turns out that you don't, and I'll show you that when I start coding. But again, in Python, the way that we like show where a function, where an if statement or a loop or a function begins and ends is just by using indentation. So wherever you like change indentation, or wherever you switch back to the old indentation you were using, that's when the compiler will know that your function or your if statement is over. I'll show you what I mean in just a minute when I start coding. All right, so I'll wait for 30 more seconds. You can continue sending me your code, and then I'll start coding. Vedant asks, why are we not learning while loop? It's a great question. I think the choice between for loops and while loops is often a choice of style. And I like using for loops, but you can totally also use while loops. You can do everything that you can do with a for loop with a while loop and vice versa. I just prefer using for loops. Okay, so I'm going to start. So what we want to do is we want to create a variable a, and I want to assign it a bit value. So I'm just going to say that a is 1, and then I'm going to say that b is 0, right? I just randomly chose those values. Then I'm going to say if, because I want to make a decision, if a is greater than b. And whenever you have these kinds of statements, you have to put a colon to indicate that you're now going to put in code which talks about what to do in case this if statement is true. You're going to start a different level of indentation. So if a is greater than b, we're going to say print a is greater than b, right? Else, and then I want to continue adding conditions. I'm going to say else if a is equal to b. So now I'm checking the case if a is equal to b. We're going to say print a is equal to b. Okay. And then finally, the only condition left is that a is less than b. So you don't need to explicitly write that. Even you can just use an else statement. So print a is less than b. And to answer your question, wait, I don't see the question anymore. Oops. Where is it?
I think it was, what's the difference between else, elif and else?
Right, okay, yes. So what is the difference between else if and else, right? So else if is used when you still want to give it a condition. So notice that here I used a equals b. So I'm still making a comparison. Else is used when you've just run out of conditions and you just want to be like, okay, if none of these previous ones are true, here's what I want you to do. So you don't give any conditions with else. You're just saying if nothing else is true, here's what I want to happen. Okay, so let's run that. And so because a is 1 and b is 0, it executed the first one. So it just printed a is greater than b. If I change these values, if I say instead that a is 1 and b is also 1, then now it's printing that a is equal to b. And finally, if I change a to 0, now it's saying that a is less than b. So what happened in this case is it first checked the first if statement, and that was not true because a is not greater than b. It then checked the second if statement, which is also not true because a is not equal to b. And so it just came onto the last else statement. And it printed out, it did whatever was said in that statement. Why can't you just replace an else if with an if? That's a great question. You can. So I can do this. And it's still going to work. The difference is that in this case, it's going to make two comparisons. It's going to first check this, and then it's also going to check this. Whereas if I do this, if I do an else if, it's only going to make one of these three comparisons. It's only going to make this one, and if this is true, it's going to skip the else if. Whereas if I just do this, it's going to make this comparison, and then it's also going to make this comparison, regardless of whether or not this first one is true. Whereas if I have an else if this first one is true, it's going to skip this else if. So that's the difference. elif is just, I think, Python format, like Python's way of writing else if. Other languages use the whole word else if. Python, I think, just uses elif. Okay. Other questions about conditionals before we move on to loops? For loops? Could I explain how to do indenting? Yes, actually, I actually meant to do that and then I forgot. So you'll notice here that this print statement, that's indented. That's it's not starting right in the left here. There's like a bit of a gap here. And most Python development tools will do this indenting for you automatically. And if you don't do this indenting, so for example, if I just do this, right? This gives me an error because it says expected and indented block. It's expecting you to indent it. And if you don't do it, it's not going to run because now Python doesn't know what goes inside your if statement and what doesn't. So indenting is really, really important. Whenever you want to change the level of indenting, what you can do is just press tab, and that's going to do it for you. And as I said, most of these softwares will just automatically do the indenting for you. You'll also notice that the if, the else if, and the else, those are all at the same level of indent. So don't change the indentation between the if, the else if, and the else. That could be one error that some of you might be getting. Okay, let's keep moving. Now let's talk about loops. So a loop is something that you use when you want to run the same piece of code again and again, or if you want to analyze the different elements in a list one by one, right? This is something that we saw in the QKD lab last week when we analyzed each bit of Alice and Bob's keys one by one, right? When we did that, we used a for loop to go over the bits one by one. So we use loops when we want to run a piece of code repeatedly, or if we want to go over the elements of a list one by one. A for loop, it's called a for loop because it just uses the word for, and a while loop, which I'm not going to do today, but it's called that because it uses the word while. When you define a loop, a very useful function is this function called range. And what range is going to do is it's going to return a sequence of numbers. So something like, let's say, let me do a quick example of that. So, sorry, I'm going to have to shrink back out to add another cell. So something like print range 5, right? That's just, oops. Or if I say something like a equals range 5, and then I say print a, right? It's, I'm somehow not able to get it to print. But what this is going to do is it's going to create numbers from 0, 1, 2, 3, 4, 5. It's going to create numbers in that range. And so that's very useful when you're.
I think you can convert it if you do list around range.
Thank you.
Because range is itself an iterator. Oh, or list like LIST.
Oh, to convert it
to a type. Okay. Yeah.
Okay, there we go. Thank you, Brian.
No worries.
Yeah. So yeah, this is just very useful for generating ranges of numbers so that you can then iterate, or you can then use those to go over your lists one by one. So we are going to be using the range function quite a bit. And if you look at the notebooks that we did in labs in the last 2 or 3 weeks, you will see this function used repeatedly. Okay, so to practice loops, okay, Claire asks, why does it not include 5 in the list? That's just, I think, a decision that the people who made that function made. So yeah, when you use range, it does not include that last element. So it's going to be 0, 1, 2, 3, 4, up until like the element that you include minus 1. Okay, so here's a question that you guys can think about. So Alice and Bob have been using QKD to build their keys. They're not very good at QKD yet, but they're just figuring it out. They're trying to get used to it. They're trying to do some QKD to distribute keys between them. And the length of the keys is 8 bits. Okay, they've decided to use an 8-bit key. Alice's key is 00110001. That's Alice's key. And Bob's key is 0010001. So I've given you values for Bob's keys. And so what Alice and Bob want to do is they want to make sure that their keys match. And so what I want you to do is just write a very simple piece of code in which you'll go over each bit of Alice and Bob's keys one by one and see if those bits match. And print if the bit matches or if it doesn't match. So let me repeat. Alice and Bob have these 2 keys that they've generated using QKD, which they're not yet very good at. And they want to compare their keys because they're just learning, they're figuring out QKD. So they want to see if they successfully did it. And so I want you to store their keys in 2 variables, Alice key and Bob key. And then I want you to compare their keys element by element and print if each bit matches or if it doesn't. Iris, yes, range returns natural numbers. There are other functions that you can use to return decimals. I'm not going to get into that here, but feel free to Google around and find functions that do the things that you want to do. So I'm going to pause for maybe another minute and let you guys code this, and then we'll code it together. Once again, you can send me your code in the Q&A as you develop it, and any questions. Okay, so I'm going to start coding this. So first, I want to define a variable called Alice key, and we're going to say that that is, let's see, what did I decide here? It is 0, 0, 0, 1, 1, 0, 0, 0, 1. Okay. Then I'm going to create another variable called Bob key, which is 0, 0, 1, 0, 0, 0, 0, 1. Okay, just checking if the lengths are the same. Now I can use a for loop to compare these keys. So I'm going to say for I in range 8, right? The length of their keys is 8 bits. So for I in range 8, I want I to go from 0, 1, 2, 3, 4, 5, 6, 7. We're going to say, oops. And then once again, you have to use a colon sign to then indicate that you're starting off with what's going to go inside the for loop. So it automatically created an indentation for me. If Alice key at the index I is the same as Bob key at the index I, we're going to say print the bits at index match. So in this case, if the bits are equal, they match. Else, we're going to just say print the bits at index do not match. And so here you'll notice that I converted the I to a string. Again, same issue as before. If we don't do this, it won't print correctly. Okay, let's run this. Okay, so it tells us that the bits at index 0 match, 1, 2, at index 3, they do not match. 4, 5, 6, 7, all of those match. So we were able to use this for loop to compare each of these bits one by one. And now imagine how much work this would have been if we hadn't been using this loop, if we had done it manually for each bit one at a time. So for loops are used to reduce the amount of code that you need to write. We were able to do this with just like 5 lines of code instead of having a separate comparison for every bit. And here we only have 8 bits, right? But I could expand this to like 100 bits and the code length would remain the same if we use loops. What does I represent, Victor asks? So I is the variable that I'm using to go over to represent each index of the keys. So you'll notice that I said if Alice underscore key at the index I is equal to Bob's key at the index I. So I is being used to represent the index that's currently being compared. I is going to go from 0 to 7. That's what we represented when we said range 8. It's going to take I from 0 to 7. Okay, any questions about loops before we move on to our last topic, which is functions? How come 3 does not match? That's just because of the way that I defined this. We can change this, so I could instead do like this. So now I just change Bob key to 0011, and now they all match. So that's just, that's just how I define them. This, for example, this could be exactly, so Fran was discussing last week, right? Alice and Bob are going to compare the first few bits of their keys to check if there's an eavesdropper. So they could exactly implement this piece of code. And if their bits start not matching, they know that there's an eavesdropper present. So one of the challenge problems for last week's lab was to implement the code for an eavesdropper. And this could be a bit of that code, is to check the first few bits of your key. And if they don't match, then you know that someone was eavesdropping. Okay, a couple of you are asking questions about like if there's more than one loop, you can totally like put loops inside loops. So then you can use different, so you would use like I for the outer loop and J for an inner loop. You can totally do that kind of nesting. It's called nesting, and you can totally do that. I won't be doing examples of that here, but yes, that's totally allowed. Okay, let's move on to our last topic, which is functions. So a function is a block of code which you can call at specific times whenever you're writing your program. So if there's a bit of code that you want to call at a specific time, you want to run that piece of code at a specific time, and also you want that piece of code to behave differently depending on what input you give it, then you can put that bit of code inside a function. So you guys might have come across functions when you study math, right? We use f of x to represent functions. So this is a very, very similar idea. You give it an input and it produces some kind of output. And depending on what input you give, the output changes. The most common way that we use functions is we put in some code inside the function that we know we'll need to use later on. And then we can call that function or use that function to implement that piece of code. Enrique, to answer your question, yes, it's the same if you use a list. In Python, strings and lists are treated very, very similarly. So you can use a list also. We've already been using a lot of functions. So the print command that you've been using, that's a function. And whatever you give it inside the parentheses, that is the input that you're giving to the print. In previous labs, you've also used functions like input or compile, execute. You've used the execute function to run quantum circuits. You've used the quantum circuit function to create quantum circuits. So these are all examples of functions. And you can define your own functions as well. The way you do that is you use this keyword called def, D-E-F. So def followed by the name of your function. So here I'm just calling it my function. And then you have to put parentheses to explicitly state that it is a function. And this is a very simple function. It just prints hello from qubit. So if you run this code block, that's just going to define the function. So there's two steps to using functions. First, you have to define it, and then you have to call it. So just defining the function is not enough. You have to call your function. So that's what is happening here. We are calling our function. And the way you do that is you just type the name of your function and then parentheses, and that just calls your function. And when I call it, it just prints hello from qubit. So it's only when you call your function that you actually use it in your code. And that's what makes functions so useful, is you can just set aside that piece of code by defining it, and then you can call it exactly when you want to use it. So as I was saying, functions can be given inputs, right, to make them behave differently depending on what the input is. And those inputs are also called arguments. So argument and input, they mean the same thing. And you put them inside the parentheses. So notice that this function did not take any inputs. But if you want to give it an input, you can just put it inside those parentheses. When you use the print statement, right, this is the input. We're putting that input inside parentheses. So that's the input to the print statement. Okay, so here's the final question for our little programming review. I wanted to create a function that's going to compare Alice and Bob's keys that we had just done in the previous question. So I wanted to create a function which will compare Alice and Bob's keys, and then I want you to call that function and compare two specific examples of compare a specific example of Alice and Bob's keys. So up here, we had already implemented this comparison. Now I just wanted to create a function which you can just call to make this comparison for you. This would be really useful, right? Because what this would mean is that you don't need to keep on writing this code over and over. Whenever you want to make a comparison, you just call this function. Whenever Alice and Bob want to check if there's an eavesdropper, they'll just use this function. Okay, so I'll wait for maybe a minute. I know that we're running a bit long. I apologize for that, but we are almost done. I'll wait for a minute. You guys can send me your code, or you can wait for me to start coding. So yeah, all that we're doing here is just creating a function which does the same comparison that we had done previously. You can call the function whatever you want. Give it your favorite name. Aris asks, we always create functions before the main function, right? So we don't use main functions in Python as far as I know. I think that's more of a C++ or C. That's how C++ and C are written usually. In Python, I don't believe that we use main functions. You can certainly call functions from other functions. You can totally do that. But you don't need to create main functions in Python the way that you might in C++ or C.
Oh, Akshay, I might be interpreting wrong, but I think the student might be asking in terms of ordering of functions. Like if it matters if you call, maybe not, but this might be a good thing to discuss if you call a function that's defined after, like,
Oh,
before.
I see what you mean. Okay, okay. Thanks for clarifying that, Fran. So yes, you always have to define the function before you call it. That needs to happen. But what you can do is if you have a code block where you're defining several functions, then the order inside there does not matter. So you can define different functions in whatever order you want, as long as the function is defined before you're calling it. That is in fact a very common mistake that I make when I'm coding, is I'll either like call a function, but I would not have run the code block where it was defined, or the code block where it's defined is like later on in my code. So yeah, you always need to define your function before you call it. Okay, let's start coding this. So I'm going to call my function compare. I'm going to borrow Javier's name. And now I want my function to take two inputs. I want it to take Alice's key, and I want it to take Bob's key, because I want my function to behave differently depending on what these keys are, right? I want it to print the bit-by-bit comparison of the specific keys that I want to give it. So just like loops and if statements, you have to end this statement with a colon, again, to specify that you've now entered the part where you're going to type out the code that goes inside the function. Okay, then I'm just going to copy the code that I had over here, because it's the same code. So I'm just going to copy this code over. One small change I'm going to make is instead of writing for I in range 8, I'm just going to say for I in range length of Alice key. So what this does is it just makes our function a bit more general. Now this function can compare keys of any length, not necessarily 8. Okay. And that's all there is to it. If you just run this block, oops, there was a problem. Ah, right, there was a problem with the indentation because I didn't indent the if statement correctly. So I'm just going to change this indentation there, because when you enter the for loop, I hadn't indented my if statement correctly. And now it's defined. And now I'm going to define Alice's key. So let's say Alice key is equal to 001. Bob key is equal to 010. I'm just using a short key. And then let's call the function. So compare Alice key, comma, Bob key. So in this statement, I'm calling my function. I'm using my function. And the advantage of giving it these inputs is that now I can change these keys and I don't need to retype everything. And so this is now telling me that for these keys, the bits at index 0 match, at 1 they don't, and at 2 they don't. And now if I change this to, let's say, 0001010, and let's make sure the lengths are the same, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's add another one. This, I was able to use the same function without having to make any changes to compare this second key. I could have used length of Bob. That's completely fair. One kind of shortcoming of my function right now is that the lengths of the two keys have to be the same. But I could have totally used the length of either one. Are variables inside a function local to that function? Yes, they are. What if the length of the keys is not the same? Then you could modify the function to account for that. You can build in some fail safes against it. Yeah. Why did the arguments have the same name as variables? Yes, I agree that that is a little bit confusing. So what you could do instead is if you want to avoid that confusion, you can give them different names. So what you could do is you can just say A, comma B. And then you have to change it consistently everywhere. I'm just calling it Alice and Bob A and B. And this will still work. Still works. So yeah, if you want to avoid that confusion, you can totally use different names. You can also use the same names, that also works. So that's kind of a style choice.
Hey, Akshay, not to put you on the spot, but maybe to relate this back to today's lecture, do you think you could tell us the big O of your compare function?
The big O of the compare function. So let's think about that. How many operations is the compare function performing? So what we are doing here is we are comparing each bit one at a time, right? And each comparison is one operation, right? For every bit, we are saying, make that comparison. And so as we increase the number of bits, I think that we are linearly increasing the number of operations. If we have 3 keys, if we have 3 bits, we are making 3 operations. If we have 10 bits, we are making 10 comparisons or 10 operations. And so I think that the big O of this function is order n. It should be scaling linearly.
Awesome. Thanks, Akshay. Just
Yep,
another example for everyone.
Yep. And I'm seeing a lot of students in the chat are also replying order n. All right, so I think that's pretty much all that I had planned. This was just a gentle reminder review of these basic concepts, and hopefully everyone feels a little bit more confident about seeing functions and loops and if statements used in the lab and homework notebooks. Definitely feel free to send us more questions on Piazza as they come up, and we will share this notebook on Canvas.
Thanks, Akshay. Have a great rest of your weekend, everyone.
All right, bye everyone. See you all in labs.